Today we're going over section 3.8 in our BJU Press Pre-Calculus textbook. We're going to take a look at rational functions. We are going to figure out how to find horizontal and oblique asymptotes for these functions. And then we're going to find holes for unreduced rational functions. And then we're also going to learn how to graph them. So a rational function is where you have a ratio. So you're going to have a function in your numerator and the function in the denominator. So what's important to note is that your function in your denominator can never equal 0 because you cannot divide by 0. So one of a really key characteristic of a rational function that's easy to tell if it's a rational function is that it's going to have an asymptote. So there are a couple of different types of asymptotes. There's horizontal, there's vertical, and there's oblique. So vertical asymptote occurs where the denominator of our reduced fraction equals 0. So you're going to take your rational function, you're going to see if you can reduce it, and then after you reduce it, you'll take your denominator and you're going to set it equal to 0. You're going to solve for x, and that will give you your vertical asymptote. Then we have what's called a horizontal asymptote. So there's a couple of different reasons that we would have a horizontal asymptote. The first reason is if our degree of our denominator, which is the bottom polynomial, if your bottom polynomial, the degree of your denominator, is greater than the degree of your numerator, then you have a horizontal asymptote at y equals 0. Which is, of course, the y-axis, right? And so, or the x-axis, I'm sorry, so it's the x-axis. If the degrees of your denominator and numerator are equal, so if the degrees of your polynomials are equal, then you have a horizontal asymptote at y equals r. And that r is going to be the ratio of the leading coefficients. And remember, the leading coefficients are the actual numbers in front of your leading term, right? So if your degree of your denominator is bigger, then it's the x-axis. If the degrees are the same, then your horizontal asymptote is at the horizontal line y equals r, where r is the ratio of the leading coefficients. So there are no horizontal asymptotes when the degree of the numerator exceeds the degree of the denominator. An asymptote that is not horizontal or vertical is called an oblique asymptote. So an oblique asymptote is actually going to be a line. An oblique asymptote happens when your degree of your numerator is bigger and the remainder is not 0. Because if the remainder is 0, that means that you can actually reduce it and simplify. So in order to find the oblique asymptote, you're going to divide the denominator by the numerator. So you're going to have to use the long division method that we learned in a previous chapter. Once you've done that, you're going to have your oblique asymptote, and it's going to be the line y equals mx plus b. So it's going to be a linear line, and that's going to be your oblique asymptote. Sometimes you have a hole in your graph, and the hole is a 0 of both the numerator and denominator. So if you have your polynomials factored in your numerator and your denominator, and you notice that 2 of the factors cancel, the a value in your factors is going to be where the hole is at. It's going to be at x equals a. So let's look at an example. We have a graph h of x, In your numerator, you have the polynomial x minus 2. In your denominator, you have x squared minus 5x plus 6. So first thing we want to do is see if this reduces. So we're going to factor our denominator. So x squared minus 5x plus 6 becomes x minus 2 times x minus 3. And then we notice that the factors x minus 2 cancels, leaving us 1 over x minus 3. But remember, that also leaves a whole because when they cancel, that a value is your whole. So x cannot be 2. There's a whole actually at x equals 2 in our graph. So we have an asymptote, right? And when we graph it, notice that at x equals 2, we're going to place a hole right there. So the asymptote was at x equals 3. So remember, in your denominator, after you reduced it, you ended up with x minus 3 on the bottom. So that is why your asymptote is at x equals 3. Okay, so let's identify domains, zeros, asymptotes, and holes of a function. So here's our function. It's actually already been factored for us, which is nice. So what can our domain not be? Remember, the domain can not be anything that is going to cause our denominator to be 0. So -5, 3, and 7 would all cause our denominator to be 0, which means that those cannot be x values. Our domain can be any x except for those x values. And since the factor x minus 3 cancels, that means we actually have a whole at x equals 3 as well. And then those remaining factors, x plus 5 and x minus 7, those tell us where our asymptotes are at. We have an asymptote at x equals -5 and x equals 7. And then our zeros are at -2 and 1. And you're like, well, why don't we have a 0 at 3? Well, that's because there is an asymptote at 3, right? So we can't have an asymptote. We can't have a whole and a 0 at the same place. So our whole is going to be at 3. And then our zeros are at -2 and 1. All right, so let's draw graphs of the following functions. So our first function, we want to do the graph 1 over x squared. So this is what that will look like. Our asymptote is going to be at x equals 0, because that's what x cannot be. And there we go. There's our graph. Okay, and let's say we want to graph 3x squared plus 1 over x squared. So when we do this, we end up being able to break apart this fraction because we have a denominator. So 3x squared over x squared plus 1 over x squared. Well, we just graphed 1 over x squared. We know what that looks like. All we're doing is we're adding 3x squared over x squared. Although those x squared over x squared cancels, leaving us just 3. So now we have our original graph that we just graphed, 1 over x squared, and we need to add 3, which is a k value, which means that all we have to do is shift our original graph up 3. Like so. Okay, so let's find our horizontal asymptotes for r of x. So remember, if the degree is the same, which they are, these are both have 4th degrees, that means our horizontal asymptote is the ratio of the leading coefficients. So our leading coefficients are 3 and 18, which reduces to 1/6. So that means that our horizontal asymptote is at y equals 1/6. Let's say we want to graph this thing. F of x equals x squared minus 4 over x plus 2. So we try to see if we can reduce it, and we can. The factors x plus 2 cancel, means that we have a whole at -2, and we're left with x minus 2, which is actually a linear graph. So when we graph it, we're going to graph y equals x minus 2 with a whole at x equals -2. So we put our whole at x equals -2, and we draw our graph. Okay, let's graph this guy. 2x cubed minus x squared minus 4 over x squared minus 3. So to order to find our y-intercept, we let x be 0, and so we end up with 4 over 3. So that's where our y-intercept is. And then we set our denominator equal to 0 to figure out where our vertical asymptotes are. And since the numerator is 1 degree greater than the denominator, we have an oblique asymptote. In order to figure out our oblique asymptote, we have to divide 2x cubed minus x squared minus 4 by x squared minus 3. We do have to do long division to do that. And then after we do the long division, we end up with the answer 2x minus 1, which means that that is where our oblique asymptote. So we're going to graph 2x minus 1, but instead of graphing it with a solid line, we're going to graph it with a dashed line to show that it's an oblique asymptote. So again, here's our vertical asymptotes. Here's an oblique asymptote. And then there is our graph.